In today's lesson, we're going to take a look at function notation. Previously, we learned what it took for a relation to be a function. That is, there was no repeated x values. Today, we're going to learn about function notation, and we owe this all to a Swiss mathematician from the late 1800s. His name was Leonhard Euler, and he came up with this notation. It's also known as the Euler notation. And this is just a simple way of writing a mathematical equation, and it's known as function notation. And you're going to see it throughout the course of the year as something that looks like this: f parentheses x, close parentheses, equal sign, and then our equation or our mathematical model. And the way that this is read, it's read as f of x. In other words, the function of the independent variable. Now, believe it or not, this was all done to avoid confusion. I don't know, if you ask me, I'm more confused already. Don't worry, we're going to get lots of practice over the course of the year. Now, another type of notation was mapping notation. Mapping notation is another form of function notation. We're going to kind of be using these interchangeably, but it replaces the parentheses and the equal sign with a colon and an arrow. And it looks just like this: g colon n arrow 3n. And it's read as the function g maps n, the independent variable, onto 3n. In other words, it's taking each input and it's tripling it. All right, so instead of using y equals throughout the course of the year, although we'll use that quite often, we are also going to use this function notation and mapping notation. So let's just take a second to kind of compare and contrast those. Here's an example equation: y equals 90 minus x. Now, this equation be used to find the complement of an angle. Well, we can change that to function notation, such as using the letter a of x is equal to 90 minus x. There's an example of function notation. The equivalent might be the mapping notation, and it would read a colon x arrow 90 minus x. Next up, we have this equation, y equals 1.8 x plus 32. Well, we might instead create the function notation t of x is equal to 1.8 x plus 32. The mapping notation equivalent would be t colon x arrow 1.8 x plus 32. So you get the idea, and you can see the pattern here. The a and the parentheses just get replaced by the a and the colon. The equal sign gets replaced by the arrow when moving back and forth from function notation to mapping notation. Our last one here, we'll actually use the letter f here. F of x is equal to the square root of 25 minus x squared. And therefore, the mapping notation would be f colon x arrow the square root of 25 minus x squared. All right. Let's get a few more terms and jump into some example problems. So far in this unit this year, we've learned that the independent variable is known as the input. It is the x value in our equation. Well, today we're also going to learn that this is called the argument of the function. And it's often seen in the parentheses in the notation, in the function notation, f of x. All right, so this x value is going to be known as the argument or the input of our function. The output or the actual value of the function for that input is known as the result. And this is going to come from actually substituting that argument in and calculating that mathematical model with that input. So let's take a look at an example. Here we have some function notation. T of f is equal to 5/9 f minus 32. This is what converts, this is actually the function that converts Fahrenheit to degrees Celsius. So here we have a temperature of 86 degrees Fahrenheit, and that is going to be our argument. We want to put it into and evaluate this function for that argument. So we write t of 86 is equal to 5/9, and now we're going to substitute 86 in for f. In other words, it is our input. All right, so 5/9 of 86 minus 32 is going to result in 5/9 of 86 minus 32 is 54. And now our output or our result from simplifying our mathematical model here will be 5/9 times 54, which is 30, so 30 degrees Celsius. So our output, or our result here, whoops, I forgot my L, is 30 when our input, or our argument, was 86. Now we can also see arguments or inputs and outputs on graphs. So in example 2, that's what we're going to turn our attention to now, is this graph here. We have the graph of this function h of x. It is -2 times the quantity x minus 1 squared plus 5. We want to evaluate h of 2. So keep in mind that 2 is my input. Now remember, your x values are your inputs. So you're going to go over to 2 on the x-axis, and you're going to go up to the graph. All right? So here's the point, 2 over and 3 up. And the output, when x is 2, or the input is 2, or the argument is 2, the output is 3. So to evaluate this, we would say that the evaluation would be 3. Now we can check that by simply substituting in 2 into our equation. So let's quick do that a minute just to check our work. All right, we substituted 2 into the x, our input. So we have 2 minus 1, following our order of operations. 2 minus 1 is 1. 1 squared is 1. That's -2 times 1 plus 5. That results in -2 plus 5, which in fact is 3. So we checked our work, and we can see that visually, that our inputs are on the x-axis and our outputs are our y values. All right, here's another example for today, example 3. Now this one gets a little bit tricky here. It says here's our mapping notation. The function f maps x onto x plus x squared over 20. We want to find an expression for f of 3n. Now our input, or our argument in this case, is not an actual value. It's an expression. But that's okay. We can take this input, 3n, and substitute it into our equation, x plus x squared over 20, wherever we see that x. So we get 3n plus 3n squared over 20. So here is an expression for what this f of 3n will be equal to. Now, we should make a note that we should simplify this as far as we can go. So 3n, I can't add to 3n squared, and I can't take 3n squared and divide by 20, but I can simplify this numerator here. This 3n squared is going to result in 9n squared. So the final simplified form should be 9n squared over 20. So 3n plus 9n squared over 20. All right, example 4 says given the mapping notation for the function p maps t onto 2 times t plus 10 over t. We want to rewrite that function using function notation. So copying those letters down, I'm going to say p of t is equal to 2 times t plus 10 all divided by t. Now we want to calculate the difference for p of 3 minus p of 6. So the tricky thing is here, we're going to actually have to evaluate this equation twice, one for the input 3 and one for the input 6, and then we will subtract their amounts. So let's first start off with p of 3. We would get 2 times 3 plus 10 all over 3. That's going to be 16 all over 3, and we're just going to leave it as 16 thirds. Next up, we have p of 6. And that's going to be equal to 2 times 6 plus 10 all over 6. Now that gives us 12 plus 10, which is 22 6. Next up, we have to subtract these two because we are going to evaluate this p of 3 minus p of 6. So that means we have to take 16 thirds and subtract 22 6. All right, if you remember way back to middle school, in order to subtract fractions, or maybe this was elementary school, you had to have a common denominator. So we need to double 16 thirds, and that's going to give us 32 6. If we subtract 22 6 from that, we're going to end up with 10 6. There you have it. There is the result of taking P of 3 minus P of 6. So a couple things we had to do there. We had to first evaluate both P of 3 and P of 6, and then we had to subtract them.